All right, here we're going to do Unit 5, Lesson 3. We're going to start talking about Euler's theorems. We talked a little bit about Euler at the beginning of this chapter, so we're going to revisit and discuss some specifics about Leonhard Euler and his theorems. So first of all, we talked about the Königsberg bridge problem, and what we have here on the left is the map of Königsberg, right? Remember this. And the idea was to travel from start at any piece of land, here I am, and be able to tour the city by crossing each bridge exactly once and ending back where I started. And we saw that this was impossible, and we're going to now discuss why. So if you take a look here, if you recall, we took the Königsberg bridge problem, the map, and we created a graph. And here's the graph on the right. Notice up here we have shore 1, and there are 1, 2, 3 bridges, 1, 2, 3 bridges connecting shore 1 on the top. And then we have island 1 and island 2, and you can see the corresponding bridges are represented by the edges of the graph. So first of all, let's talk about Euler's theorems and what he did with them. And the first thing we have to remember is we have two different types of things that we're going to look at. The first thing is an Euler circuit. Okay, now I know a graph has an Euler circuit. An Euler circuit means you can start and stop at the same vertex and hit every edge exactly once. That is, if you can do that with a graph, that's called an Euler circuit. Then we also have an Euler path, and this is right out of the reading. And an Euler path, you start and stop at different vertices and hit every edge exactly once. Okay, so really the difference between a circuit and a path is in a circuit you start and stop at the same vertex, and in a path you start and stop at different vertices. Okay, so just the fact that you're starting and stopping at different vertices or same vertex, that's the difference between a circuit and a path. Now, if you go through the reading, we can tell when we look at a graph, we can initially tell whether it's going to have an Euler circuit or an Euler path. So let's discuss a little bit how we can tell. So I know that a graph, let me get rid of these underlines here. I know that a graph will have an Euler circuit if all vertices have an even degree. If every vertex in the graph has an even degree, then I know that there exists an Euler circuit. And that makes sense. I'm going to draw a quick graph here that has an Euler circuit. So here's a graph, and we'll do that. What the heck? We'll put a double edge here. Okay, so actually, and do another double edge. There we go. So I know that this graph has an Euler circuit if I just look at the degree of each vertex. So this first vertex, remember, has two edges touching it, so that has a degree 2. The second one has a degree 2. This one has a degree 4, and this last one has a degree 4. So notice every vertex here has an even degree. And the reason that I know that there will be a circuit is if you think about it, if there's a way into a vertex, there's a matching way out of the vertex. So if there's two ways to get into a vertex and two ways to get out of the vertex, there's going to be an even number of edges touching that. So if there's one way in and one way out, still that would give a degree of 2. So what we want to do is you want to think about having a way to get back out or back off of the vertex. So once you hit a vertex, is there a way to get back off of that vertex? So that's for an Euler circuit. An Euler path, I know that a graph has an Euler path if there are exactly two vertices with an odd degree. Okay, so if there are exactly two vertices that have an odd degree, then I know for a fact that there will be an Euler path, which means I can go around the graph and I can hit every edge exactly once, but I just can't stop where I started. Okay, so that's really the difference in the reading. You should have picked up the difference between a circuit and a path is that. So now that we got a little bit of vocabulary down, next video we'll go on and we'll do these problems, and then you'll be on your way.